So hello everyone, today we're going to have hypothesis test on single sample. So this still addresses the course outcome applying statistical methods in the analysis of data. From the previous discussion, the results and a few other similar calculations are summarized in the table. The critical values are adjusted to maintain equal um, values for n is equal to 10 and n is equal to 16. So taking note that the acceptance region is from 48.5 to 51.5. So let's observe what would happen if we're going to widen it to 48 to 52. As we widen the acceptance region, alpha, or the probability of committing a type 1 error is decreased. While for beta, well, we have not computed for the other values, but just for the concept of explanation, it increases the chance of committing type 2 error. So when we widen the acceptance region, we lessen the probability of committing type 1 error, but we increase the chances of committing type 2 error. If we increase sample size from 10 to 16, increasing the sample size decreases alpha. So same is true with beta. So it's advisable to increase sample size. So just to summarize all of those comments, the four important points are the size of the critical region and consequently the probability of type 1 error can always be reduced by appropriate selection of critical values. So we select critical values. Type 1 and type 2 errors are related. A decrease in the probability of one type always results in an increase in the probability of the other. So they are somewhat inversely related. An increase in the sample size reduces beta, provided that alpha is held constant. When the null hypothesis is false, beta increases as the result or as the true value of the parameter approaches the value hypothesized in the null hypothesis. The value of alpha decreases as the difference between the true mean and the value of beta decreases as the difference between the true mean and the hypothesized value increases. So generally, the analyst controls the type 1 error probability. When he or she selects the critical values, thus, it is usually easy for the analyst to set the type 1 error probability at any desired value, since the analyst can directly control the probability of wrongly rejecting the null hypothesis. We always think of rejecting the null hypothesis HO as a strong conclusion. So if it happens that we are rejecting the null hypothesis, we are creating a strong conclusion. So the classical method in hypothesis testing, we have a fixed significance level. This is a widely used procedure in hypothesis testing and is used to use a type 1 error or significance level at alpha is equal to 0.05. This value has evolved through experience and may not be appropriate for all situations. Most of the time, if you are a starting researcher, you always make use of 0.05 as a level of significance. This is the widely used level of significance, 0.05. On the other hand, the probability of type 2 error is not a constant but depends on the true value of the parameter. It also depends on the sample size that we have selected, because type 2 error probability is a function of both the sample size and the extent to which the null hypothesis HO is false. It is customary to think the decision to accept HO as the weak conclusion unless we know that it is acceptably small. So we fail to reject null hypothesis is preferred than accepting the null hypothesis. So the statement is always to not to reject the hypothesis or fail to reject the hypothesis and not accepting the hypothesis. It does not necessarily mean that there is a high probability that the null hypothesis is true. It may simply mean that more data are required to reach a strong conclusion. So you want to, if your study is failing, if you fail to prove a certain point, then that's the time that you recommend for a bigger sample, which might result into a different outcome or would result to your required hypothesis. The power of a statistical test is the probability of rejecting the null hypothesis HO when the alternative hypothesis is true. So this is computed as 1 minus beta. This is interpreted as the probability of correctly rejecting a false null hypothesis. As an example, consider the propellant burning rate problem. Suppose that if the burning rate is less than 50 centimeters per second, we wish to show that this is a strong conclusion. The hypothesis would be stated as the null hypothesis equal to 50 against the alternative that mu is less than 50. In formulating one-sided alternative hypothesis, we should always remember that rejecting HO is always a strong conclusion. Consequently, we should put the statement about which it is important to make a strong conclusion in the alternative hypothesis. In real-world problems, this will often depend on our point of view and experience with the situation. So it's better to relate that to real-life applications. Let's have this example. A real estate agent claims that 60% of all private residences being built today are three-bedroom homes. To test this claim, a large sample of new residences is inspected. The proportion of these homes with three bedrooms is recorded and used as test statistic. State the null and alternative hypothesis to be used in this study and determine the location of the critical region. So we have two hypotheses, the null hypothesis and the alternative hypothesis. For the null hypothesis, the claim is 60% and it is about the proportion. So P is equal to 60% or 0.6. The alternative hypothesis would be a contradiction to this hypothesis. So if we want to reject the hypothesis or the claim that it is indeed 60, we use the alternative that the proportion is not 60. So the critical region would be somewhere outside the acceptance region. So outside the confidence interval. So it would be below the critical value or below the critical value and above the higher critical value. P-value. P-value is the smallest level of significance that would lead to rejection of the null hypothesis with the given data. This has been adopted widely in practice to avoid difficulties by a fixed level of significance testing. So we calculate the probability that your null hypothesis would be rejected. And you usually compare this against the 5%, the 1%, or the 10% level of significance. But we can still use the 5% level of significance. So in comparing the hypothesis test and the confidence interval, there's a close relationship between the test of hypothesis about any parameter, say theta, and the confidence interval for theta. If the closed interval from lower to upper is a 100 times 1 minus alpha percent confidence interval for the parameter theta, the test of size n of the hypothesis is h null equal to theta sub o, and h1 is equal to theta not equal to theta o. This would lead to the rejection of h null if and only if theta null is not the 100 times 1 minus alpha percent confidence interval from the lower to upper limit. A confidence interval provides a range of likely values for mu at a stated confidence level. Hypothesis testing is an easy framework for displaying the risk levels, such as the p-value associated with specific decisions. When we test hypothesis, it is important that we have to identify the parameter of interest. Check whether we're checking for the mean, the proportion, or the standard deviation and variance. After identifying your parameter, you state the null hypothesis HO and contradict that as an inequality. So the null hypothesis is a statement of equality. So you contradict the null hypothesis by an inequality so that you would be having your alternative hypothesis. You compute for the test statistic and state the rejection criteria for the null hypothesis and compute. After that, you draw conclusion. But basically, you just need to specify the test statistic, whether it is a right tail or lower tail, and then the critical region for the rejection. Examples. In each of the following situations, state whether it is correctly stated hypothesis and if there's a problem, let's check why. So mu is equal to 25 against mu is not equal to 25. So this is valid. This is a parameter, mu, equal versus not equal. So this is a valid statement of hypothesis. This is wrong. The null hypothesis should be equal, and this should be an inequality. Letter C. This is not a parameter. This is a statistic. So it should be a statement about the population mean. So that should be mu. So null hypothesis should be a statement about the population. D, P is 0.1 against P is 0.5. So the alternative hypothesis should be a statement about, it should be the same. So the alternative hypothesis must be an inequality. And letter E, so the error here is, this is S, which is a sample statistic. So it should be sigma. These are the references used for this study.